Hi everyone, my name is Kaveh. In this presentation, I am gonna talk about applications of reinforcement learning in robot path planning, more specifically using deep reinforcement learning for path planning in teleoperation applications. I did this project during my postdoc in the Control and Robotic Lab of ETS University in Montreal. This is a joint work with Professor Bonev at Automation and Manufacturing Department of ETS University and Professor Desrosiers from Software and IT Department of ETS University. First, I will give you an introduction to teleoperation. Teleoperation is the extension of a person's sensing and manipulation capabilities to a remote location. A teleoperator includes a master device where the human operator supervises the operation and a slave device which is the robotic manipulator and feedback sensors. A communication service will connect the master and slave. The human operator needs a good telepresence. By telepresence, I mean enough information from the slave environment to be able to perform a reliable and efficient teleoperation. We can divide the current robotic teleoperation systems into two categories, bilateral and unilateral. In unilateral teleoperation, user only receives visual feedback, but in bilateral teleoperation, operator also receives a full or partial force feedback of the robot in the slave environment. Bilateral teleoperation gives more sense of teleoperation to the user. However, it needs extra and expensive sensors on the slave and extra actuators on the master device, which also makes the master device bulky and uncomfortable. On the other hand, unilateral teleoperations are usually cheap and very light, but gives only visual feedback to the operator, which most of the time is not enough to do a robust and reliable teleoperation. Next, I'm going to talk about different path planning methods for teleoperation. One method for path planning is manual path planning, in which the operator is responsible for the whole path planning process. And another approach is semi-automated path planning, in which an algorithm in a computer helps a user to generate the robot path. So the user only gives high-level information about the path, and the algorithm will make the details of the path. In bilateral teleoperation, user easily can use manual path planning because user has enough information about the slave environment. But in unilateral teleoperation, which is our focus, user needs a semi-automated path planning because user doesn't have enough information to avoid collisions in the slave environment and to do an optimal path planning. So what are the challenges for a semi-automated path planning? The first challenge is that classic path plannings are too slow for real-time applications. The second challenge is that robots usually are not anthropomorphic, so it's not easy to map the human movements to a robot. And the third challenge is that path planning is a nonlinear and non-convex problem, especially when we have collisions in the we need to do obstacle avoidance in the slave environments. And the fourth challenge is that if you want to use modern methods for path planning, like reinforcement learning, it's not easy to apply them on a real robot. So we need a simulation environment. And what are the highlights of our work? In our work, we did simulation to real reinforcement learning. By that, I mean that we trained our model in a simulation environment, and then we tested the robot we tested the reinforcement learning model on a real robot. Second is that we did real-time implementation of deep reinforcement learning. And not many people did it on a real robot, a real-time implementation, because it's not easy to communicate with industrial robots without delay and in real time, especially when you are using a deep learning model, which needs a lot of computations. And third, We use deep reinforcement learning with a dynamic goal. Most of these deep reinforcement learning methods in the literature, they use a fixed goal for the robot, which means that robot's goal is to reach a fixed point. But in our application, the robot needs to follow a path, so we define it as a dynamic goal. Next, I will give you a background about reinforcement learning and the method that we used here to train our reinforcement learning model. A reinforcement learning process includes an agent which is interacting with the environment. The agent applies actions to the environment and receives observations and the reward. Based on the observation and reward, agent tries to train its policy to receive as much as possible accumulative rewards during an episode. In our case, the episode is one session of path following in our Tele-operation model. And here we used a PPO method, which is a proximal policy optimization, which is one of the state-of-the-art methods for training reinforcement learning models. Here we define our problem as a two scenario, reaching task and path following. Because path following or dynamic goal scenario is not easy, and it's not easy to train the model in this scenario. First we trained our model on a static goal, and then we extended to dynamic goal. As you can see in this figure, in a static goal, the initial and the destination position of the robot are fixed, but they randomly change during different episodes. But in a path following scenario, our goal is moving during an episode. So here you can see the whole process of training and the inference of our model. We trained our reinforcement learning model on multiple parallel simulation environments. For simulation, we used bullet physics plus a ARX model. And then we applied this trained model on a real robot. The hardware setup of this project includes an industrial robot, an ABB industrial robot, and the HTC Vive device. HTC Vive includes two controllers, which gives a 60 position of user hand, and a headset. We use the headset to give the user a visual feedback from the robot in a virtual reality environment. And we use the controllers to extract the 60 position of the human hand movements, and then this position will be mapped to our reinforcement learning model or path planning model to the robot movements. Here, as you can see, the position of the 60 position of the user hands along with the joint value of the robot will go to the policy network, and the policy network will give the speed command to the robot through EGM system, which is a real-time communication system in ABB robots. And here you can see the results of turning the robot model in a simulation environment. As you can see, when we used a different number of parallel workers or parallel simulation environments. As you can see, when the number of parallel workers increases, our model converges faster. But when the number of parallel workers are less than 10, our model doesn't converge at all. And here we compared the PPO method with older methods of reinforcement learning, and as you can see, PPO method outperforms all of them. Thank you.